In lesson 5, we're going to take a look at scaling and unscaling. So looking at the relationships between the areas of the figures like we talked about yesterday, and then the scale factors. So first thing that we're going to take a look at is this transatlantic building, which is an 853-foot tall building in San Francisco that was built in 1972. So it's this triangular pyramid building here in these pictures. The people of San Francisco were actually initially pretty upset and said that a building in such a weird shape had no place being in San Francisco. But it was actually designed for environmental practicality. So in order to let, like it says here, natural light and airflow reach the already crowded streets of San Francisco. So to kind of like open up some of the space around it and let light in. So there are 48 usable floors, okay, up until about right here. And so there's office spaces for insurance and financial jobs. And so it goes up to floor 48. And then there is this 212 foot spire that has this beacon of light at the top. So you can see it in this picture. So there's this light at the top that you can just see all around San Francisco. So let's take a look at this building a little bit further. Okay, so here you can see some of the floors, like the cross section. So here's the building being built. So, you know, as they're building each floor is like a cross section of this triangular pyramid. And then each floor gets smaller and smaller as you go up, okay, so that it's going up to this point where ultimately that light is, and then there's no space. So usable floors, like I said, up to 48, then they kind of get too small to do anything with. So there's no office spaces up there. So if we take a look at the first floor here, okay, so we've got the first floor. The dimensions of the first floor are approximately 53 meters by 44 meters. And then as you go up to the 48th floor, okay, that's a scale factor of 0.32 from the first floor. Okay, so that's a dilation of 0.32 from the first floor. So let's go ahead and figure out the area of that 48th floor. Okay, so go ahead, figure out the area of that 48th floor and explain your reasoning or show your work on page 233 of your textbook. So a couple different ways you could have tackled this. One being that you actually scaled the floor. Okay, so you could have taken that scale factor and so we know that these ones times 0.32 would give us our new dimensions. So 53 times 0.32, and you could have gotten about 17 meters for this length, and then 44 times 0.32 and gotten about 14 meters, and then found the area that way by doing 14 times 17 and getting approximately 238 meters squared. So that's one way you could have tackled the problem. Also could have done finding the actual area of the first floor by doing 53 times 44 and getting 2,332 square meters for that one. And then multiplying by the scale factor squared here. Okay, so multiplying by 0.32 squared. So 0.32 squared is 0.1024. So taking the area of the first floor, 2,332, and then multiplying by 0.32 squared, or that 0.1024, and then getting approximately 238 meters squared that way too. Okay, so either way, whether you wanted to scale the lengths by multiplying by K or scale the area by multiplying by K squared would have been fine. So let's take a look at, we've got a triangle here, okay, and the triangle's area is 100 inches squared. Then we've got a dilated version of the triangle, okay, dilated at a scale of 0.25. So my says the dilated triangle's area is 25 square inches. And Lynn says the dilated triangle's area is 6.25 square inches. So if you're in class, write this on a Post-it note. If you're at home, you can write it in your book. So decide if you agree or disagree with each person, okay? If you agree with them, explain why you agree. And if you disagree, explain what the student could have done better or the mistake that they made, okay? So I agree with Mai or Lynn because he or she did this. Or I disagree with Mai or Lynn because he or she did this. He or she should have done what? So pause the video, talk about that, or write that down, then come back. All right, so the correct answer would be Lynn's, okay? So what happened is Mai actually multiplied by just the scale factor. So she took 100 times just the 0.25. And what she should have done was multiplied by the scale factor squared. So Lynn actually did the scale factor squared. So K squared is 0.0625. Okay, so Lynn actually multiplied the 100 times that K squared value of 0.0625 to get this. So Mai only multiplied by K, not by K squared. All right, so then now using that idea for number 2, calculate the area of the figure if we change the K value. Okay, so now the K value is changing to the given value. So let me get rid of this original K value here. Okay, so now they're changing these K values. So go ahead and calculate the dilated area given those new K values. Pause the video and then come back. All right, so we've got the original area is 100, and then we remember we will multiply by the K value squared for each of these, and that will get us our new area. So in this first one, your K value is 9. So we'll be doing 100 times 81. And so you will get 8,100, so 8,100 inches squared if we dilated by a scale factor of 9. In this second one, we did a scale factor of 3/4. So now you could do it as 3/4 as a fraction. You could also do 3 divided by 4 in your calculator and get 0.75 as a decimal. Okay, so then you could have done 100 times, and then do 0.75 squared, which is 0.5625. And then times that by 100, and you would get 56.25 inches squared. So this one's actually smaller since that scale factor is less than 1. All right, then let's take a look at an application. So we've got an artist here who has drawn a 1-foot square painting. Now she wants to create more paintings of different sizes that are all scaled copies of her original. So either larger or smaller than her original. The paint she uses is expensive, so she wants to know the sizes she can create using different amounts of paint. So suppose the artist has enough paint to cover 9 square feet if she uses all of her paint. By what scale factor can she dilate her original painting? So think about the paint, okay? So the paint is covering the space. So that's what's covering this whole thing. So that's an area amount. So what scale can she change the length and the width by if she's got an area of 9? Okay, so she's got 9 square feet she can cover versus the original, which was 1 square feet. Okay, so her original dilated area was 1. Okay, which then the scale factor of that is 1 as well. Remember that the area factor is k squared and the scale factor is k. So that's just square rooting these numbers. Okay, so then this would be square root of 0, which is 0. Square root of 4, which is 2. Square root of 9, which is 3. And square root, of 16, which is 4. To go backwards. Okay, so if she has enough, if she has 9 square feet of paint, okay, so she's got 9 square feet of paint, she can change the scale of the sides by 3. So the scale factor that she can change by is 3. And then we already completed the table here. So now use your completed table, okay, to graph this. So remember, this was 0, 1, square root of 4 was 2, square root of 9 was 3, square root of 16 was 4. So plot these on this graph paper. So let me get a little bit of a thicker dot here. All right, so we'll plot these. So 0, 0. Okay, 1, square root of 1 is 1. Then we went to 4 is 2. 9 is 3. 16 is 4. And then we'll just connect these with a smooth curve. Okay, so graph your data. This is also a filled in version of this is also on page 237. So if you don't have graph paper, if you're at home, this graph is on page 237. So you can look there to help you. So now use your graph or your table to estimate how much she could cover if she had 12. Okay, so if she had 12 square units of paint, so in this first column or in this x-axis, she's got 12 square units of paint. What scale factor would that be? So you could look in this table and say, all right, well, 12 is between 9 and 16, so it's going to be somewhere between 3 and 4. For the scale factor, you could also remember how we got these scale factor values, which was by square rooting the area. Okay, so then you could square root the 12 to figure out a more precise scale factor. And so square root of 12 is equal to 3.46 or 3.5. And you can look on this graph as well. So the graph, if you go out to 12 and you follow 12 up until it hits the line, and then you follow over and see that it's at 3.5. So an area factor of 12 would give us a scale factor of 3.5. So suppose the painter has enough to cover 1 square foot and she buys enough paint to cover an additional 2 square feet. Okay, how much does this change the scale factor that she can use? Okay, so she has currently enough paint for one scale factor, or for 1 square foot. And now she adds an additional 2. Okay, so that means she's got enough for 3 for the area. So we would do that first before going over to the scale factor. So now she has 3, enough to cover 3 square feet in area. So then we could do a square root of 3 to get 1.7 for the scale factor. Because these were both area measures. So her k squared that she has enough for is 3. So square root that and get 1.7. Then suppose that she had enough to cover 14 square feet, and then she buys an additional 2 square feet of paint. So now again, those are both your area measures. So she can cover 16 square feet of paint. So then your k value is going to be the square root of that, or 4. So, and then we were supposed to compare. So in this one, her original that she had was 1. So then her k value would have been 1. So how much does that change? 1 to 1.7 versus her 2 in the k squared. So now she went from 14, okay, and 14, the square root of 14 would be 3.7. So when she went up an additional 2 square feet here, it gave her an additional 0.3 on the k. Versus here, when she went up 2, she went from a k value of 1 to k value of 1.7. So she went up 0.7. Okay, so how does it change the scale factor? So she went up in both, okay, but went up more, got to go up more in this one than this one. So an equation that we could use is that y equals the square root of x, okay, because our one side is k squared and our other side is k. So that would just be square rooting. So the expression that can put those together is the square root of x. And when we calculated the difference in 2 square feet of paint, were those rates the same? Okay, and if you remember in the first one, we went from k equals 1 to k equals 1.7. And then we went from k equals 3.7 to k equals 4 for an additional 2 square feet of paint. So this one went up by 0.7 and this one went up by 0.3. So their rates are not staying the same. So it was a larger jump between the 1 and 3 square feet of paint than it was for the 14 and 16. And so you can see that when you look in the graph. So if we look at the graph here, from 1 to 3, okay, so you're looking at this chunk of the graph, that's steeper than the graph from 14 to 16, so it kind of flattens out here. So if I grabbed this one and moved it over here, you see how it's a flatter slope than it is right here. So the rate of change is higher here, okay, and it flattens out in this curve, okay? So it starts out with a really steep difference or rate of change, and then as you continue going with the square root graph, it continues to flatten out. All right, so let's take a look at if we understand the lesson. So suppose the painter's original painting is 2 square feet and she has enough to cover, enough paint to cover 72 square feet. So we've got the original area and now we've got the new area. So can we find the scale factor? So if we take the new area divided by the original area, this will give us our area factor. So this is our k squared. Okay, how many times bigger is the new area? 36 times bigger. That's our k squared. So then our k, we would square root that. So our scale factor is 6. Our original painting can be dilated at a scale factor of 6. So then let's just look at some possible dimensions here. So if we have an area of 2 square feet, that means length times width needs to be 2. Okay, so I'm just going to use a 1 and a 2. So 1 times 2 is 2. So now if we scale this, okay, a dilated image so that we can get this 72. So we just found out that our scale factor would be 6. So then we can multiply each of these sides by 6 to get our new dimensions. Okay, so take your scale factor, multiply the sides. So multiply by 6, multiply by 6. Then if we found this new area, 12 times 6, that would give us 72, which again then is k squared times bigger. So that's 2, the original area, times the scale factor squared. 6 squared was 36. 2 times 36 is 72. All right, so we know that we can work backwards to find scale factor. So if we know how many times bigger the area is, that will give us our k squared factor. Okay, so that'll give us our area squared. And then we can just square root it to end up with our k. So if 64 is our k squared, then we can just square root it to get our k. So you can just read through here and it's talking about that you can use a graph. Okay, so if this was our area of our shape, then this would be the scale factor. So if this is our area factor, then this is our scale factor. So these are our k squareds. So these are our k's. We can see that on the graph here. So y equals square root x is our graph that represents that. Okay, as we square root each of these, we'll get the scale factor. Some things to notice, the rate of change is not the same. Okay, so it starts really steep and then it starts to flatten out. The left side of the graph, so over here, is steeper. Okay, and to the right, it's flatter. Okay, so as you go to the right, it gets flatter. As you go to the left, it gets steeper. So changing drastically, more drastic here on the left, and changing less quickly on the right.